Hello everyone, myself Vivek Jagirgar, sixth sem student in Department of Electronics and Telecommunication Engineering, Bangalore Institute of Technology. Today I'll be demonstrating multimedia communication assignment projects which we have done through MATLAB programs under the guidance of Dr. N.J. Girish Kumar sir. So let's get started. The first uh, question what we have is explain and implement Huffman dynamic or adaptive Huffman coding in MATLAB for data compression. Simulate the compression and decompression of any sample text and calculate compression ratio. So before actually getting into the exact code, let us have a brief introduction about what is Huffman coding, why it is used and its importance and some applications. So basically Huffman coding is a type of lossless data compression algorithm which we can use for reducing the size of the data, whether it may be a text or image, without losing any information. After compressing, also we obviously we get the reduced size, but the thing is we don't lose any data, any bit of data. So and we have two types. One is static Huffman coding, and another one is the dynamic Huffman coding. And in dynamic Huffman coding, there are algorithms which we have which we use tree structures, data structures like left node and right node to calculate its bit stream and all those things. And what is its importance? So efficiency achieves near optimal compression for any symbol based data, reducing storage and bandwidth needs. So one is the efficiency and another one is the lossless thing and some storage advantages. And applications used in zip files, gzip files and other achieving tools for compression files, whatever we use in our Windows to compress or decompress things, those are based on these techniques only. And multimedia like JPEG, MP3 audio compression also, it's a efficient type of encoding and decoding technique. Let's get into the exact code, what we have. So according to our syllabus, we have dynamic Huffman coding. So first so this is the main thing which we have like alphabet. If the alphabet K is the alphabet that we insert, and if it is less than 20, we have K minus 1 bits which we represent in E plus 1 bits, and if it is greater than 20, then we have K minus R minus 1 number that we represent in E number of bits. Left node is greater than the right node, then we should have to swap those things. So this is a function which may swaps those two uh, child elements. So here I will enter my name. So it will generate the symbol and the corresponding code word. Like for example, for V, so here V is inserted for the first time. The one represents the NYT code, and the remaining 001 represents the fixed code. So this is the combination of the NYT code as well as the fixed code. So for V, it's 1011. For I, it's 001000. And V, it is only one because V is repeated again. So it's inserting for the second time. So when the symbol is repeated, we don't follow the NYT code. We just follow the way towards the fixed code. So that's why it's one, and E is repeated for the first time. It is NYT code followed by the fixed code, and similarly towards the K. And the original size 40 bits, because here we can see VIVEK total is 5 letters. So 5, and each letter carries 8 bits of data. So 8 into 5, that is 40 bits of data. And the compressed size, so the compressed size is 26 bits. So the compression ratio, that is original size divided by compressed size, that we get is 1.54. This is the compression ratio of the data. So this is the program what we have in our syllabus. But in this, there is a small thing that we are not able to decode the same text. If we go to decode the same text, we are not able to generate the same data what we have inserted. So that's why we have modified the code, generates the which also generates the Huffman tree, like how we can actually visualize. So let me show you. So I'll just run the program. So here it is asking to enter the text to compress Bijapur. So the original text is Bijapur. And finally, this is the tree. And here we can see the original size is 56 bits and the compressed size is 20 bits. The compression ratio is 2.80. And we got the same text what we have inserted, that is Bijapur, and we got the decompressed text also Bijapur. So it's also displays the original text and the decompressed text. Basically, we have included here to string compare if the text what we have inserted and the text what we have got, if both are equal, then it will print decompression successful, original and decompression text matches, else it will say that decompression text will fail. So these are the function associated with it. Four, step 5, step 6, and this is the final step what we have got as the final code structure Bijapur. So it also creates a basic tree structure. Actually, it should be from here to here. It should not go up to here. It should be like here only. But this algorithm follows. Sorry, this we have used the inbuilt function, that is tree plot, which is used for the tree data structure. The similar one we have used here. That's why that didn't stop here only. It will along it extend up to the base code. So that we have is simulate differential pulse code modulation for audio compression in MATLAB. Record or load an audio signal, apply DPCM and reconstruct the signal, analyze signal distortion and compression efficiency. So basically DPCM stands for differential pulse code modulation, which is basically a lossy compression technique for audio signals. It predicts each samples based on the previous one, encodes the difference and quantizes to fewer bits. Basically, what it has a very high compression efficiency, easy to implement for in real-time applications like real-time audio signals. Also, it is easy to apply and balance compression and distortion. So the error rate is very less in these type of things. And application, telephony, audio encoding, video compression, embedded systems like IoT devices, wherever the audio we are transmitting. So there we can use these types of pulse differential pulse code modulation compression techniques. So let's get into the code. So here I'll run this program. Hello, myself Vivek from Bangalore Institute of Technology, studying in the Department of.
Hello, myself Vivek from Bangalore Institute of Technology,
So
studying in. Hello, myself Vivek from Bangalore Institute of Technology, studying in.
so this is the original signal. This is the reconstructed signal. Both are almost same. And here what we have the reconstructed means the original and the reconstructed. This is the error. So almost the amplitude is 1 to -1. That is almost two two values. But here we have got error is almost negligible, like 0.05. So these are the original signal, reconstructed signal, and this is the error. Though whatever we have given as the input will be stored in the original dot wave audio file,
Hello, myself Vivek from Bangalore Institute of Technology, studying in.
and this is the
Hello,
reconstructed audio file.
myself Vivek from Bangalore Institute of Technology, studying in.
Yeah, thanks. The third question is about simulate motion estimation and compression for video compression in MATLAB. Load a video or frames, compute motion vectors using block matching, and reconstruct the predicted frames. So basically, the motion estimation is a video compression technique that identifies motion between the frames by computing motion vectors. Basically, between the two vectors, it identifies wherever there is a motion among those frames. Like it basically divides the whole frame into uh, different type of blocks, and then to each block, the previous frame to the next frame, it identifies the motion, and based on that motion, it compresses the frames. So what is its use is to reduce the data size by encoding motion vectors and residuals, basically the differences. Instead of applying the algorithm on full frames, it only applies wherever there is the motion, exploiting temporary redundancy in the videos. So that's the most important thing. In bitrate lowers bitrate for video storage and transmission, maintains visual quality with minimal data, and foundation is like core MPEG and H.264 formats. Also, it can encode. Application video compression broadcasting like digital TV, satellite transmissions, and video conferencing, whatever we use Cisco, WebEx, Zoom calls, Skype for real-time compression. All those things, motion estimations are used. File manager where we can select which video we want to decompress. So I'll select this sample resize because I have saved in 128 into 128 pixels. So I've selected the video. So here, as you can see, video loaded successfully, reading frames. So basically, yeah. So video loaded successfully, reading frames. So it will read 10 frames, each of 128 into 128 pixels, and performing motion estimation on 9 frames and motion estimation complete. So it took 0.89 seconds to analyze this video. And compression analysis, average mean square root is 22.16, average peak signal to noise ratio is 41.0 dB. The original size is 131072 bits and motion vector bits are 9296 where the motion is captured, and the residual bits is approximately 54154 bits, and estimated compression ratio is 20.68. And the result what we have will be saved in the motion estimation.png what we have here. So this is the original frame what we have given as the input, and these are the residuals from each frame. And here we can see the motion vectors, like here there is no, for example, if I click here, here we can see XY 72, 8 and UV minus 80. And here we have the motion vector as 120, 8 minus 8 and 0. Here we have 56, 128 minus 8 and 0. So these are the motion vectors. And using that, this is the predicted frame what we have got. And both original frame and predicted frame are almost not, almost 99% same. So, and the next program what we have is compare uniform and non-uniform quantization technique for audio compression using MATLAB. Simulate both methods on audio file and evaluate impact on audio quality. Basically, uniform quantization divides the range into equal intervals step by step, mapping samples to the nearest level. Whereas the non-uniform uses lower amplitudes and larger amplitudes. Based on the amplitude, it will divide the compression technique. For example, you have external audio and we are giving speech. So external audio has a larger amplitude and the speech or the audio what we have is a lower amplitude. So basically it selects the lower amplitude and based on that it will make the compression. This is signal to noise ratio of an audio critical in telephony. As we know, while telephone or any conference call, the first thing you need to maintain the quality and there should not be any miss errors, and we have less data to transfer, so that's why we need less data, high quality and same speed. So the external amplitudes will be removed and the lower amplitude, whatever the speech signal will be there, that will be taken care. And application, as we can see here, telephony, PCM, that is pulse code modulation, ADPCM, adaptive differential pulse code modulation, and other audio formats like MP3, AAC speech compression. We are using this uniform and non-uniform content code. And I have given a test audio. I have input. So we have given test audio as an input to this, and based on that, it will give the uniform and non-uniform quantization. So here I'll just run this program. So this is the original signal, that is audio what we have given. This is non-uniform signal. This is uniform signals. So as you can see here, it divides step levels. So as you can see, this is the original signal. There is no, based on that, it will divide into the levels, each level, and this non-uniform, it divides based on its amplitudes. So as you can see here, these are the, it has taken the average as you can see here, it is based on amplitude levels, and these are based on the segment levels. So this is the uniform quantization error for this, and this is the non-uniform quantization error for this. Next question we have is implement 2D DCT based intraframe video compression in MATLAB. Basically, the DCT quantization and inverse DCT compare the original and reconstructed frame using PSNR. So basically, 2D based compression. DCT stands for discrete cosine transform, which is used to transform image blocks into frequency coefficients. And the main aim is to reduce the video frame size by discarding less predictable high frequency details, enabling efficient storage and transmission. And the importance is it has a high compression with good visuals. We are not compromising over the resolution or quality of the frames or the video, but we are compressing the size of the file. And the foundation of the core is JPEG formats, MPEG, .h264, basically MP4 formats, and all those things. And flexibility, adjustable quality via quantization. If we do more apply quantization on this, we can change the quality as well. And application JPEG, MPEG, H264, H265 quality, compression and decompression. And these are used in the YouTube and Netflix, whatever, while streaming according to the net speed, the video quality will be adjusted. So for that real time adjustment streaming purpose, we use this 2D DCT, and for storage and digital cameras also, we can use these kind of application compression and decompression technique. So here we have the code. I'll just run this. So I have so here I have given the I have added the sky.mp4 in the same folder, and that's why I have mentioned sky.mp4. So the program will read this video file. So we have got here video loaded successfully because the video is rendered properly, and we can note the video duration is 16.05 seconds. The video frame rate is 29.97 FPS. So therefore, the total number of frames is 480. And the video height is 720 and the video width is 1280. So according to that, the algorithm adjusts the height and width of the video. So here you can see the frame size. 720 is the height, 1280 is the width, and here 10 and 3. So these are a frame rate, and 10 basically represents the number of frames. So if we go and apply the algorithm for all the 480 frames, it will take a long time to evaluate all those things. So what I have implemented is, for example, if the video is for 30 seconds, I'll divide the whole video into 10 parts. So basically 3 seconds uh, per. So I'll take the first frame of those 3 seconds. For example, if the video is of 30 seconds, then I'll equally divide that video into 10 parts, and I'll just take the first frame out of that. So here, as you can see here, this will display automatically one after the other, original frame and the reconstructed frame and the compressed one. 9 and 10. So video loaded successfully, and these are the So these are the pre-frame PSNR values. The frame one has a PSNR value of 45.25 dB, which is absolutely very great. And the second almost, because that's a video and it's almost the same video, so that's why the those these PSNR values are almost same. As you can see, 45, 46, 45.44.65, and the average PSNR is 45.38 dB. And the original bit size is 221184,000, and the total compressed size of the video is 74168. So estimated compression ratio, it's 30.97. So it is compressed almost 30 times. So that is what we have the advantage of 2D DCT. So all these frames will be saved into the MATLAB folder. As you can see here, reconstructed 1024 up to 10, and these are the original frames. And These are the compressed frame. I'll just show you in the folder. Frame. This is the compressed frame, and this is the reconstructed frame. So as you can see, the original frame and the reconstructed frame have same quality, same resolution, and the compressed, this is the compressed one. This is the original one. I'll just full screen this one. This is the original. This is the compressed into the dot format. What we that is basically the 2D DCT matrix format, and this is the reconstructed. So as you can see here, this is the original frame, which is taken at 7.13 seconds of the video. This is compressed frame, these are the DCT coefficients basically, and this is the reconstructed frame 5. Original frame, compressed frame, and this is the reconstructed frame. So these are the coefficients of the DCT. So the next question what we have is compare and contrast lossless and lossy image compression using MATLAB, PNG using PNG and JPEG formats. So basically lossless compression is done through using PNG, where the quality of the data is maintained and there is no loss of data. So that's why it's a lossless compression. And when we use JPEG formats, it's a lossy compression. Some part of the information can be maybe maybe we can lose it. So because it's almost used in sharing purpose, JPEG, and PNG is used in the production purpose image. So basically, I have taken the original frame what we have generated in the last program, that is original frame. Through the video we have taken 10 frames. Out of the 10 frame, I am taking just one frame, that is original frame 1.png. I have given this as an input. So let's clear the command window and let's run the program. So as you can see here, this is the original image, that is original frame one what we have taken from the video, and that the same frame I have given input to this compression. And here is the JPEG, which is PSNR having 66.8 dB, which is having the same quality, that is 90. And this is the same picture which is having lesser quality, that is 50. So the PSNR is 41.6, which is actually lesser than the, obviously it, as quality reduces, the PSNR reduces. And this is the same file which is having the PSNR of quality 10. So and again the PSNR value reduces to 32.4 dB. As you can see, the quality of the picture also drops. And uh, the original uncompressed file size is 2764855 bytes, and this is lossless, that is PNG, that we have got 300977, which is almost 9.91 compression ratio. And this is JPEG, which is having the quality of 90. We got the compression ratio as 45.16 with a PSNR of 96.88, which is actually a good uh, decibels. And JPEG, which is having 50% quality, that have reduced 98.54 times. So which is having 2764854, it's compressed to 28084, which is having 98.54 compression ratio. And another one which we have reduced to 10%, that is which is 18192 byte, which is compression, which have the compression ratio 151.98, and with a PSNR of 32.54. We have all these details will be saved into this file called compressions, that image compression, lossless versus lossy. Next thing we have is arithmetic coding. Arithmetic coding is a type of lossless compression algorithm for text string into a single fractional number. Through this we generate a tag or encoded bit string which can be used for communication purpose. So it is why it is used means for same compression purpose. And its importance is Huffman coding for small alphabets or skewed probabilities. Through this arithmetic coding, we can have different probabilities. Through the probabilities also, we can work out on the string files. So we can compress those also. And multimedia such as JPEG 2000, H264, And while transmission of data like network protocols and all, so we can use this arithmetic what we have. I'll just clear the window, just run the program. So input text. For example, first I'll give my name, VIVK, Vivek. So original text is Vivek. Enter custom probabilities as vector. For example, uh, we have our own probabilities like V is having a probability of 0.3, I is having 0.2, which results in 1. But as of now, we are not giving any custom probabilities. So the algorithm will assume this as a string and it calculates its own probability. Like for example, V is repeated twice. So it's calculate automatically the number of frequency and all those things. So I'll just enter. So as you can see here, probability model with cumulative frequency. So first we'll find the CF. So E is 0.2, I is 0.2, K is 0.2, but V is repeated twice. So therefore the probability is 0.4. And these are the ranges like 0 to 0.2, 0.2, 0.4, 0.2, 0.6, 0.6 to 1. And whatever the lastly we have get is tag, basically that is the encoded number. So we'll get 0.73210000. Estimated bits needed, that is 11. So decoding step. So first V is encoded, so that will be in the range of 0 to 1, and then I 0.621, and third one, that is V, again it will go to 0.68 to 0.71, and finally K, we have the range lower limit as 0.7280 and upper limit uh, 0.7344. So basically using these two, we'll find out the fact that is lower limit plus upper limit divided by 2, and we'll get it as 0.7312. And the decoded text is Vivek, and the original text and decoded text perfectly matches. And regarding the compression statistics, the original size is 40 bits as we have 5 characters in my name, and each letter carries 8 bits of data, so that is 8 fives of 40 bits. And the compressed size is here, what you have got is 11 bits. So the compression ratio is 3.64. So another example I would like to demonstrate using the probabilities, that is went star, whatever there is in our textbook, went star or went dot. So W is having a probability of 0.1, E is given with a probability of 0.3, N is given with a probability of 0.3, T is given with a probability of 0.2, and the star is given with a probability of 0.1. So as you can see here, the encoded tag, we got the same as in the textbook, that is 0.81611, and these are the probability range. E is from 0 to 0.3 according to the alphabetical order, 0 to 0.3, 3 to 6, 6 to 8, 8 to 9, and 9 to 1. These are the ranges of the cumulative frequency, and these are the bit needed for the estimated bits. And decoding step, first W will be sent, so it goes from 0 to 0.1, and then E 0.8 to 0.9, 8.9, and these are the steps. And finally when we input star, we get the lower limit as 0.8114 and the upper limit as 0.8162. So both will be added and divided by 2, we'll get the tag. And the original size is 40 bits, compressed size is 14 bits, compression ratio is 2.86. And all these statistics will be saved in the compression stats.txt, as we can see here. Arithmetic coding compression results. Original text is went dot, encoded number is so our tag is 0.8161. These are the probabilities, these are the decoding steps, and this is the compression statistics. And the next program we have is the wavelet based image compression. So wavelets are basically the transforms to decompose the image into frequency components. Using the frequency components, we analyze the image and then we compress through different wavelet families while preserving the same quality. And importance, balances compression ratio and quality Adaptable via wavelet choice. We have different wavelet families through which we can compress those uh, videos, and different wavelet families suit various image types and application. Modern image and video decodes medical imaging. So these are the importance, and applications are same, like JPEG 200, WebApp, and image medical imaging like CT scan, MRI scan. We use these wavelet functions to compress those images, and remote sensing like satellite imagery and multimedia like video compression techniques and all. We can use this wavelet based image compression techniques. So let us have the demonstration. So here I have given the input as original frame 1, which I've generated from the video. So I'll just run this program. Graph which is generated by the code, like we have mean square error through that. These are the wavelet families like HARR, DB4, SMP4, COF2, COIF2. These are the mean square root through the different wavelet families, in which we have HAAR, which is having the least mean square root error, and DB4 is having a little high. Both that are all negligible because that are into 10 to the power minus 6, which are very less error. But till then, among the four, HARR is having least error. Coming to the PSNR, same, her has having the highest PSNR, and remaining all are almost same, like 50 decibels of. This is the using the COIF2. This is the original image, and this is the reconstructed image. Both are having the same quality but having reduced sizes. And this is using the SYMP4, and this is using the DB4 wavelet family, and this is using the HAR, that is her wavelet family. So these are the things what we have executed in the MATLAB as an assignment project, which gave us very good understanding about our multimedia communication subject, about what are the compression techniques, what are the different types of techniques, and how they actually decompress the things. Practically, we have understood those things using these simulations and all. So thank you one and all. Thank you, sir. Thank you so much.